All right, in this video, we're going to talk about the manipulation of K, the equilibrium constant, how we manipulate it. There's 3 ways. All right, and so let's use a real example. My real example will be hydrofluoric acid plus water going to H3O plus F minus. All right, and so we have hydrofluoric acid is an acid. It's a bronzosyluric acid, so this H is going to donate here. All right, and so that's our products and reactants. Now this is reversible. It has a K. K would be the concentration of hydronium, concentration of fluoride, all over the concentration of hydrofluoric acid. Now, a little note here. Solids and liquids are omitted from the equilibrium constant expression. They are omitted, all right? And they're omitted because their concentrations do not change measurably, if that makes sense. We're not going to measure, like, okay, I have, 1.25 milligrams of sodium, calcium carbonate, and you're not going to measure that differently, right? Even here, water, how did the volume change a little bit? Very difficult to measure, and it doesn't, for all our purposes, not worried about it. All right. And so now for this reaction, K is equal to 6.3 times 10 to the negative 4. All right. And so if we're 6.3 times 10 to the negative 4, what does this tell us about this reaction? Well, negative 4 means that we are small. 1, 2, 3, 6, right? We are pretty small. We're smaller than 1,000th. All right, so that means there's going to be more HF in solution than H3O plus and F minus. So the denominator is bigger. Okay? So the first manipulation is if we reverse the reaction, right? You invert K. Well, if I reverse the reaction, I would have H3O plus fluoride going to hydrofluoric acid and water. Our equilibrium constant would be concentration of hydrofluoric acid all over hydronium and fluoride, which is the inverse of this one, right? It's just flipped. So K would equal 1 over K, 1 over 6.3 times 10 to the negative 4, which this K would be 1.6 times 10 to the third, which kind of makes sense, right? Which means, in this case, looking at the reaction from this point of view, it will make sense that we have more of these in solution and less of those. In the original equation, we have more reactants than products. But since we flipped the reaction, we have more products than reactants. And that just makes sense. All right. The second manipulation would be if you multiply coefficients by a factor, we raise K to that factor. Well, what do we mean by that? So we go back to our HF, hydrofluoric acid, and water. Get hydronium and fluoride. If we put a 3 in front of this, K now is hydronium to the third power. Fluoride to the third power. Because everything's to the third power. And HF, hydrofluoric acid, to the third power. So K equals 6.3 times 10 to the fourth to the third power. So K in this case, which I don't have this written down, 6.3 times 10 to the negative, it's negative 4. I put a negative in there. Negative 4. I would have 2.5 times 10 to the negative 10th. In this case. All right? So, why would we do that, you might ask? Well, the third way to manipulate K is that if adding multiple reactions, you multiply Ks. And you might, right? So what do you mean by that? If I have reaction 1, right? We add those up, you get a new reaction. The new K would be K1 times K2 and K3. Right? Because this would have a K, this has a K, and each reaction has an equilibrium constant. So to put that in perspective, real example, HF plus H2O, hydronium, fluoride, new reaction. Let's say we have H3O plus OH minus gives you 2H2O liquid. All right, if we were going to add these up to get a new reaction, all right, well, what cancels? All right, one of the H2Os cancel and hydronium cancels if I add them up. And so we would have HF plus hydroxide going to fluoride and water. And this would be equal to our 2Ks. .3 times 10 to the negative 4 multiplied by 1 times 10 to the 14th. 6.3 times 10 to the 10th, right? Which now this makes this reaction product favored. Like 6.3 times 10 to the 10th is a big number. You would pretty much drive anywhere in the country, maybe even go to other countries to get that amount of money in pennies, right? Because that'd be a lot of money, right? It's a huge number, right? That's how I can tell if it's a big number. Would I want to drive all the way across the country to get that many pennies? If the answer is yes, then it's a big number, right? Maybe not that many pennies because I don't have a vehicle to carry them all, but like that much money worth of pennies. right? So that's how I can tell if it's a big number. All right, so those are the three manipulations of K. Now, so we know equilibrium can be expressed, right, in terms of concentration. And that would be molarity. Or pressure. And that would be atmospheres. And so we're going to now add Kp, and that's with pressures, is going to be equal to Kc for concentration times RT to the delta N. All right. R is the gas constant. T is the temperature. All right. In Kelvin. All right. So we got temperature in Kelvin. We got the gas constant. What is delta N? Delta N is the change in moles. All right. So if we think about the change in moles, all right, that would be, all right, the sum of the coefficients of products minus the sum of the coefficients of reactants. So it can be 0, right? It can be 0, it can be 1, it can be -2, it can be any of those, all right? And so it does not have to be, it's almost always going to be a whole number, but it's not going to be a fraction, but it can be anything. Now, the gas constant, just, I don't know what one you think it is, but we have concentration and pressure. So the gas constant with those units would be 0.08206 liters times atmospheres moles Kelvin. So that would be the gas law we have with that. All right. So that is the equilibrium constant in a nutshell. All right. Hopefully that makes sense. And we'll see you in the next one, guys. Take care.